This week we're going to start a discussion of corrosives, which for the most part are acids and bases. Although, as we talk about here on this slide, there are a few things that could be categorized as corrosive that aren't really fitting the category of acids or bases. But basically in this chapter and in this week's modules, we're going to be focusing on acids and bases. And so one thing here on this first slide is that there are some different definitions of what a corrosive is, depending upon whether you're talking about RCRA, the Resource Conservation and Recovery Act, which defines one category of hazardous waste is corrosives. Those of you that have had a class on haz waste will remember that there are some different characteristic, what we call characteristic hazardous waste. So you can be a hazardous waste based upon whether you're listed, whether the particular chemical or waste stream is listed in the regulations, or whether it exhibits certain characteristics. And one of the characteristics that can cause a chemical to be classified as a hazardous waste is its pH. So on this slide, we've got two different definitions. One is DOT and one is RCRA, and these are both discussed in your textbook. So notice the DOT definition. So a corrosive under DOT is going to be a liquid or solid. Notice that it specifically talks about liquids or solids that causes the full thickness destruction of human skin. So in other words, there's nothing in that DOT definition that mentions pH. Okay, it talks about you can be a hazardous waste because it destroys your skin upon contact. Or the other way that something could be a hazardous waste is it destroys steel or aluminum surfaces at a particular rate. Now the fact is, if it destroys steel or aluminum surfaces, it's probably also going to destroy your skin. Why would they be worried about steel or aluminum surfaces? Why would DOT specifically be worried about a material that could destroy steel?
Because they're being transported in vehicles made out of it.
Remember what DOT is about. It's the Department of Transportation. You're concerned with shipping hazardous materials. And how do you ship a lot of hazardous materials? In steel drums or aluminum containers. Well, you obviously don't want anything that could destroy those containers. And so if this material in contact with steel or aluminum destroys that metal at a rate greater than 0.25 inches per year, then it's going to be considered corrosive. What's really interesting is DOT doesn't talk about pH, only talks about its effect on either your skin or upon metals. But under RCRA, we do talk about pH. So RCRA talks about a corrosive as something that has a real low pH, meaning it's an acid, and they define that to mean something that has a pH less than or equal to, and if you notice here, it's a less than or equal to 2, or a real high pH, meaning it's a base, with a pH less than or greater than or equal to 12.5. So on the ends of the pH scale. If it's in the middle, if it's between 2 and 12.5, then it doesn't meet RCRA's definition of a hazardous waste, which is probably fortunate because if you were to test the pH of a can of Coke, what do you think it would turn out to be?
3 or slightly lower?
Yeah, maybe 4, somewhere in that neighborhood. And why would it be acidic? Why would a can of Coke be acidic?
Because of the carbonation.
Okay, for 2 reasons. It's a carbonated beverage, which means that it has dissolved CO2. They have carbon dioxide gas that they bubble through the liquid, and the liquid absorbs some of that CO2 gas. And as we're going to see in a little bit, when CO2 reacts with water, it produces carbonic acid. So it is a weak acid because of the CO2 that's dissolved in it. But then if you look at the label on the can, it also says that Coke contains phosphoric acid. So in fact, Coke, Pepsi, doesn't matter, they're all on the acidic side, but they're not going to be meeting the definition of a corrosive under RCRA, because it's going to be greater than 2, which is pretty good. It'd be hard to sell Coke if you met the definition of a hazardous waste as a corrosive material. Okay, so what we're going to do in the next couple of slides here is to move from legal definitions under DOT and RCRA to chemical definitions of acids and bases. So you should have seen this when you took your general chemistry class. And it turns out that there's different definitions of acids and bases in chemistry. One of the oldest definitions is the Arrhenius definition of an acid or base. And what you need to know about the Arrhenius definition is that's assuming that you're in an aqueous solution. So you have to have water present in order for you to talk about the Arrhenius definition. So the Arrhenius definition of an acid is something that produces H3O plus, the hydronium ion, when it dissolves in water, and a base is something that produces hydroxide ion when it dissolves in water. Okay? So that means if you're not in water, you can't use this hydronium or this Arrhenius definition. And in organic chemistry and in gas phase chemistry, there's an awful lot of times that we don't have water as a solvent. And so this is the most limited definition. We can only apply it in certain conditions. But we do an awful lot of things where we use water as a solvent. And so when we do, this is a perfectly adequate kind of definition. Oops. So in this particular example, you can see that this compound HX, whatever that is going to be called an acid because when it reacts with water, it produces the hydronium ion, and B, whatever that is going to be a base because it produces hydroxide ion. So some examples here would be hydrochloric acid, HCl, which dissolves in water to produce H3O plus and chloride ion. So HCl we would call an acid, an Arrhenius acid, because it's producing H3O plus. And ammonia here is going to be a base because it reacts with water to produce ammonium ion and the hydroxide ion. Okay? So anything that produces hydrogen ion, hydronium ion, H3O plus, or hydroxide ion is going to meet the definition of an Arrhenius acid or base. Now, a slightly more general definition is called the Bronstedlowry definition of an acid or a base. And here we talk about protons, okay? So that means that in order for something to be called a Bronstedlowry acid, it has to contain hydrogen, because a Bronstedlowry acid is a proton donor, and a Bronstedlowry base is something which is a proton acceptor, okay? So notice this doesn't include water. You can have a situation where you don't have any water present, and you can still talk about it as an acid-base reaction as long as you've got a proton present. So an example here is going to be the same thing we saw before, where we had HCl. HCl is going to be a Bronstedlowry acid because what happens is that it's donating a proton to water to form H3O plus, and then what's left over is the chloride ion. And ammonia is going to be a base because it's a proton acceptor. It accepts the hydrogen ion from water and becomes an ammonium ion. So the same equation, HCl plus H2O, can be analyzed either in terms of being an Arrhenius acid or base or in terms of a Bronstedlowry acid or base. Anybody notice anything kind of weird about these two equations? The two that are written up there?
Water is an acid and one in a base in the other.
Exactly. So in the first case, what's happening is water is accepting a proton. So that makes it a Bronstedlowry base. And in the second case, water is donating a proton. So that makes it a Bronstedlowry acid. Can you have something that's both an acid and a base? Well, must be able to. I just wrote those two equations down there. Something that can either be an acid or a base is called amphoteric. Sometimes it's also called amphiprotic, but let's just use the word amphoteric. So that means it's a compound that in some instances can act as an acid, in other instances it can act as a base. It has the ability to do either one. And when you think about it, what that means is that if you mix water with something that is a stronger acid, in other words, water has a certain tendency to donate a proton, but it's not a very great tendency. It's a very weak acid. So when you mix it with a strong acid like HCl, then the HCl wins. The HCl donates the proton to water. And so then water's acting as a base. But if you mix water with a weak acid like ammonia, then water wins. Water has a stronger tendency to donate a proton to the NH3 than the other way around. So then water's acting as an acid. That's what an amphoteric material is all about, okay? Now, what's important about the Bronstedlowry definition is that this is more general because you can apply this concept even in cases where you don't have any water as a solvent. Notice we're not talking about the definition of an acid as something that generates H3O+. Here we're talking about the definition of an acid as something that donates a proton, and a base is something that accepts a proton. Well, what is the form? What's the physical form of pure HCl, pure hydrogen chloride? It's a gas. At room temperature, HCl is a gas. And what's the form of ammonia at room temperature, NH3? It's a gas as well. At room temperature, atmospheric pressure, ammonia and HCl are gases. So it's possible for us to take HCl gas and ammonia gas and react them together in the gaseous phase, no water around, okay? And when we do, we see a reaction. In fact, if you have a tube where you're bringing in HCl on this side and ammonia on this side, in the middle of that tube, what you're going to see is a white solid being formed. So HCl is a colorless gas, you can't see it. Ammonia is a colorless gas, you can't see it. But when they react together, you get this white solid. What's the white solid? It's ammonium chloride, okay? And so that's an acid-base reaction, even though we don't have any water present. Now, if we take HCl gas and bubble it through water, then we get something called hydrochloric acid. And if we take ammonia gas and bubble it through water, we get something called ammonium hydroxide. And we can have different concentrations of hydrochloric acid depending on how much HCl we bubble through, and different concentrations of ammonia. Concentrated HCl means that the water is saturated with HCl. You can't get any more HCl to dissolve in the water than what you have in concentrated HCl. And at room temperature, concentrated HCl is about 12 molar. So if you see a bottle of concentrated hydrochloric acid, like in the lab, that's about 12 molar. And if you see a bottle of concentrated ammonia, that's about 15 molar. All that means is that you can't get any more. You could sit there all day long and bubble more ammonia through it, but the water's saturated, it won't absorb anymore. So when they're dissolved in water, we call it hydrochloric acid. When it's just pure HCl, we call it hydrogen chloride, okay? So if we talked about the reaction between hydrochloric acid and ammonium hydroxide, I can talk about the Arrhenius definition. But if I'm talking about gas phase reactions, then I have to talk in terms of the Bronstedlowry definitions, okay? Now there's a third definition, and that's called the Lewis definition after a guy named Gilbert N. Lewis. Remember the Lewis electron dot structures we talked about? Same Lewis, very famous guy. He was the chairman of the chemistry department at Berkeley back in the 1930s. Berkeley was a pretty big hotspot for chemists back in those days. Still is, for that matter. But he was very involved in developing some of the fundamental ideas about bonding and about acids and bases and things. So he came up with the Lewis definition of an acid or a base. And notice what the Lewis definition says. Doesn't talk about hydronium ions, doesn't even talk about protons. He talks about a Lewis acid is something that can accept a pair of electrons, and a Lewis base is something that can donate a pair of electrons. So you don't even have to have a chemical that has hydrogen in it in order for it to be an acid or a base under the Lewis definition. It has to have hydrogen in it if it's going to be a Bronsted acid, because it has to donate a proton. But it doesn't have to have hydrogen in it in order for it to be a Lewis acid, because here we're just talking about donating or accepting a pair of electrons. So let's see how that works. So here's an example, aluminum trichloride, AlCl3. So if you look at the periodic table, it turns out that aluminum is in group 3. So aluminum has 3 valence shell electrons. That's it. It's in group 3. Now, how many valence shell electrons does chlorine have? It's in group 7 in the periodic table. It's a halogen. So how many valence shell electrons do halogens have? It's not a trick question. All the halogens have 7 valence shell electrons. They need 1 more. So whether it's fluorine, chlorine, bromine, iodine, doesn't matter. They all have 7 valence shell electrons. They're looking for 1 more electron. So where could they get 1 more electron from aluminum? Well, you could bring a chlorine right up here, right? So the chlorine's got 7 valence shell electrons. It shares an electron, forms a covalent bond with the aluminum, and now the chlorine's happy, right? And we can do that with these other 2 electrons. So this electron can react with chlorine, and this electron can react with chlorine. So all 3 of these chlorines around the aluminum have 8 valence shell electrons, because they only needed 1 more, and they each formed a covalent bond with aluminum, so they're happy. But what's wrong with that electron dot structure?
Aluminum only has 6.
Aluminum only has 6, and it wants 8. So it turns out that aluminum chloride is very reactive. And the way it reacts is it wants to grab 2 electrons from something else. It wants to form bonds where it gets 2 more electrons so that it can have 8 electrons around it. So under the Lewis definition, if it's grabbing 2 more electrons, is that going to make it a Lewis acid or Lewis base? The Lewis acid says it accepts a pair of electrons. So aluminum trichloride turns out to be a very strong Lewis acid. Would you be able to describe AlCl3 as an acid under the Arrhenius definition? Would it be under the Bronstedlowry definition? It's not an acid under Bronstedlowry because it doesn't have a proton. Doesn't meet that definition. So the Lewis definition is actually the most general definition. You can apply the Lewis definition under virtually any circumstances. And it turns out that the Lewis definition is very useful in organic chemistry, because there's a lot of times in organic chemistry where we're following what happens to electrons, and it's not necessarily a proton that's being moved around, it's the electrons that are being moved around. So for example, oh, here we go, hold on a minute, just a second. So if we look at this reaction down here, just a second. My eraser's not working. Oh well.
Oh, I didn't click keep, so now it's not.
Oh, okay.
Not making me erase.
Okay. There we go.
Well, no, I mean, like, after you click keep, it locks it in, no matter how many times you exit and re-enter.
Oh, really?
Yeah.
Okay. All right. Well, anyway, take a look at this reaction here. AlCl3 plus chloride ion, Cl minus. Do you think the aluminum trichloride would have a tendency to react with a chloride ion? Well, the chloride ion has 8 electrons around it, right? It's pretty happy. You know, like sodium chloride, that chloride ion is pretty happy. Sodium chloride is not very reactive. We eat it in our food all the time. I mean, it just kind of sits there. The chloride ion doesn't do anything because it's pretty happy. But if that chloride ion were to see an aluminum trichloride molecule, that aluminum trichloride wants one of the lone pairs of electrons, the non-bonding pairs of electrons on that chloride ion, can be donated to the aluminum. And we can get a molecule called, or an ion called AlCl4 minus. Okay? And now, if we look at the electron dot structure around AlCl4 minus, now the aluminum has 8 electrons around it because it took 2 electrons that were non-bonding from that chlorine to form a covalent bond. The chlorine still gets to count them because it's covalent, right? And the aluminum now gets to count. So that would be the way we would explain this reaction is the aluminum trichloride's acting as a Lewis acid. It's accepting a pair of electrons. The chloride ions acting as a Lewis base. It's donating a pair of electrons, okay? Another thing that happens a lot is that we have carbon-carbon double bonds in organic chemistry. So remember that a double bond in organic is composed of the sigma bond and then the pi bond by overlap of 2 electrons on each carbon atom that are in p orbitals, that pi bond. And that's a weaker bond. It's easier to break than that carbon-carbon single bond in the sigma bond. But that's a source of electron density. They're not lone pairs of electrons. They're not non-bonding pairs of electrons like they were on the chloride ion. But nevertheless, it's a source of electron density. So what do you think would happen if you took aluminum trichloride and reacted it with an alkene, where you had a carbon-carbon double bond?
The aluminum would bond to one of the carbons?
Yeah, it might go after that pair of electrons in the carbon-carbon double bond. And you think of that as basically an acid-base reaction. So we're not going to get involved in all the organic chemistry. If you go back and remember anything from organic chemistry, aluminum trichloride was a catalyst. It was a Friedel-Crafts alkylation catalyst. We used it quite a bit in organic chemistry to make things, and we were taking advantage of the fact that it was a Lewis acid. Okay, so it's just one example of a molecule that doesn't even contain a proton, yet still is considered to be an acid. What do you think would happen if I reacted aluminum trichloride with water? Let me do this reaction. It wants a pair of electrons, right? Where is there a pair of electrons in the water molecule?
On the oxygen?
Yeah, remember oxygen's got 6 valence shell electrons. So 2 of those electrons are used to form bonds with a hydrogen. So you have 2 OH bonds, and you've used up 2 of the 6 electrons from oxygen. What about the other 2? The other 2 pairs, the other 4 electrons on that oxygen atom? I mean, the water looks like this, right? It's got 2 pairs of non-bonding electrons on that oxygen atom. So if you were an aluminum trichloride and you saw a water molecule, what do you think you'd do?
Grab the electrons?
I'd go after that lone pair of electrons on the oxygen, okay? And so what ends up happening then is that the aluminum, so this is aluminum trichloride, wants to form a bond to that oxygen, and what ends up happening then is that a hydrogen comes off, and we have an aluminum trichloride with a hydroxide ion attached to it, and it generates a hydrogen ion. So in water, if you dissolve aluminum trichloride in water, it becomes acidic to pH paper, okay? And in fact, what's going to happen is you can actually replace all of those chloride ions with OH bonds and generate hydrogen ions. So aluminum trichloride in an aqueous solution could be a Bronsted base because it's accepting, actually, no, it wouldn't be a bronze. Would it be a bronze? That's a good question. That'd be a good question for a quiz. Would aluminum trichloride reacting in water meet the definition of a Bronsted base?
No, because it's accepting OHs rather than H's.
Yeah, remember, a Bronsted base is something that accepts a proton. Is the aluminum trichloride accepting a proton? Would AlCl3 have any reason to accept the proton?
No.
It's short of electrons. A proton doesn't have any electrons. So there's no, you add a proton to aluminum trichloride, it didn't want that. It wants to go what's bound to that proton, where there's a pair of electrons left over, okay?
But it is an Arrhenius acid.
It would be an Arrhenius acid because it would generate a H3O plus, right? All right, so now we want to move to a definition of strong versus weak acids. So the idea is that we've got some acid, let's just call it HX, whatever the acid happens to be, HX. And we're going to react it with water. So we're going back now to aqueous solutions. So for the rest of this module, we're going to be talking about aqueous solutions. So if you react an acid with water, the acid's going to tend to donate a proton and generate H3O plus, right? So there's the reaction. To define that as either an Arrhenius acid or it could equally well be a Bronsted acid. Now, the question is, does this reaction necessarily go to completion? In other words, if there's an equilibrium constant for this reaction, is the equilibrium constant very, very large so that the equilibrium lies very far to the right? Or is it a weak acid where maybe a little bit of it gets donated, but not all of it? And that's the difference in definition between strong and weak acids. So in a strong acid, what happens in this equilibrium is that essentially all of the HX disappears. All of that hydrogen from the HX is donated to water to form H3O plus, and then what you have left over is X minus, whatever X is. So in a strong acid, you don't have any HX anymore in water. What you have is H3O plus and X minus. So examples of strong acids would be things like HCl, H2SO4, HNO3, perchloric acid, HClO4. These are all what we call strong acids. And so in water, they are all completely dissociated. That hydrogen ion is essentially completely transferred to the water molecule. And so what you really have is H3O plus and a chloride ion or a nitrate ion or a perchlorate ion. Okay? That's a strong acid. In a weak acid, that reaction doesn't go to completion. Some of it gets transferred to water, so we have a little bit of H3O plus, but we still have some HX left at equilibrium. And so when we're talking about an equilibrium, then the first thing we want to talk about is an equilibrium constant. So what is an equilibrium constant? How do we write equilibrium constants? K equals what? Products over reactants. So the concentration of each of the products divided by the concentration of each of the reactants raised to whatever their coefficient is. Now in this case, the coefficient is just 1, so it's just H3O plus to the first power, X minus to the first power. Sometimes you might have a different coefficient of other. So we'll see some examples of that. So the idea is that a strong acid, you don't really talk about equilibrium constants. The equilibrium constant is essentially infinity. And so for all practical purposes, we say, for example, if I say I have 1 molar HCl, I have a 1 molar solution of hydrochloric acid. What I really have is 1 molar H3O plus and 1 molar Cl minus. Okay? It's completely dissociated. I don't need an equilibrium constant. But if I have 1 molar HF, for example, it turns out that's not a strong acid. The equilibrium constant Ka for HF is about 10 to the minus 4. What does 10 to the minus 4 mean in this equation, that equilibrium constant equation? If this equilibrium constant is 10 to the minus 4, what does that mean? Which is bigger, the products or reactants? If the equilibrium constant is 10 to the minus 4. Reactants, right? So in other words, it's a fraction. I don't have as much product as I do reactants. So at equilibrium, there's going to be more HF present than there is H3O plus and F minus. There's going to be a little bit of H3O plus. So if you tested a 1 molar solution of HF with litmus paper, it would turn red. There's some hydrogen ion produced, but it's not completely dissociated. So to actually calculate the hydronium ion concentration, you have to use the equilibrium constant expression, and we'll do that in the next module. We'll go over. So on this next table, this is a really important table. You're going to want to bookmark this, or maybe you've got a different textbook that you want to use. This is just one example of a table of acid dissociation constants. So here's my acid, HA. So what's happening is that acid is losing a proton, and so A minus is whatever you get when you pull a proton off. So if I have hydroiodic acid, HI, then what I get when I pull a proton off is I minus. If I have H2SO4, like in sulfuric acid, then what I get left behind is HSO4 minus, the bisulfate ion. Okay? Excuse me. So, now on the next column there, you see a table of Kas, and Ka stands for acid dissociation constant. Okay? So you see that for these up here at the top, the Kas are very large. 10 to the minus 11, 10 to the minus 9, 10 to the, not minus, 10 to the 11th, 10 to the 9th, 10 to the 7th. So those are such big numbers that for all practical purposes, we can say that the acid is completely dissociated. And so in fact, we say there's not really any difference in concentration of the hydrogen ion, whether you have HI or HClO4. If you have a 1 molar HI concentration and a 1 molar HClO4 concentration and a 1 molar HCl concentration, they're all 1 molar in hydrogen ion concentration. There's no real difference, even though the Kas vary a little bit, because they're like 10 million or 100 million, something like that. So those are what we call strong acids. And for strong acids, things are easy because you don't need to use equilibrium constants. But now we get down in this region where we're talking about acid dissociation constants that are in the negative realm, -3, -4, -5, all the way down to -10, -11. Now, what does a 10 to the minus number mean when you're talking about the equilibrium constant?
Fraction.
It's a fraction, so it means the numerator is smaller than the denominator. So that means there's going to be more reactant at equilibrium than there is product. And the smaller that number is, the less product you're going to get. So this table is decreasing acid strength. As you go from top to bottom, the acid strength is getting smaller. So if I ask you which is the stronger acid, all you have to do is to look at this table. The stronger acids are going to be on top and the weaker acids are going to be on the bottom. So if I ask you benzoic acid, see where benzoic acid is here? Here's benzoic. And phosphoric acid. If I ask you to compare benzoic and phosphoric acid, which would be the stronger acid?
Benzoic.
Nope. So it goes, as you go down, the acid strength decreases. So the Ka for phosphoric is going to be 10 to the -3, and the Ka for benzoic is going to be 10 to the -5.
Phosphoric, parentheses 2.
Yeah, so phosphoric is H3PO4. So it turns out you could pull all three of those hydrogens off. So the phosphoric one means pulling the first hydrogen. So that's, when I say phosphoric acid, I'm really referring to H3PO4. That's why you were just looking at pulling it off of one of the secondary or tertiary hydrogen. Okay, so as you go down that column, the acid strength decreases. So if I ask you which is the stronger acid, all you got to do is look at a table like this and see whether it's on top or on the bottom. Now, what's that column on the far right? It says pKa. What do you think that is?
That's the logarithmic function of it.
Right. And when we talked about pH, what was our definition of pH? pH equals the negative logarithm of the hydrogen ion concentration. So what do you think pK is going to represent?
The negative logarithm of the Ka.
Right. So here we go. pKa means negative logarithm of Ka. So let's just take something that's easy. Remember that the logarithm is the 10 to the exponent. So whatever that exponent is, that's the logarithm, the common logarithm. So if I have a 10 to the -5, what's the pKa of 10 to the minus 5? 5. So the logarithm would be minus 5, right? Because that's what the exponent is. But the p means it's the negative logarithm. So minus a minus 5 would be plus 5. And conversely, then, if I have a pKa, or excuse me, if I have a Ka of 10 to the minus 10, what's the pKa? 10. So which is the stronger acid there? An acid with a Ka of 10 to the minus 5 or an acid with a Ka of 10 to the minus 10? The stronger acid. The stronger acid is the larger equilibrium constant. 10 to the minus 5 is a bigger equilibrium constant than 10 to the minus 10. So the stronger acid means you have more products, fewer reactants at equilibrium. It's more completely dissociated. So if you have an equilibrium constant of 10 to the minus 5 versus one that's 10 to the minus 10, the one at 10 to the minus 10 doesn't go very far. In other words, at equilibrium, if the equilibrium constant is 10 to the minus 10, there's not very much product. It's mostly reactant. Okay? So an equilibrium constant of 10 to the minus 10 is a weaker acid than an equilibrium constant of 10 to the minus 5. But the pKa is going to be 5 versus 10. So when you're comparing pKa's, the larger and more positive the pKa, the weaker the acid. Okay? So it's a little confusing there because of that negative logarithm. So if you go back and look at this table, you see that the pKa's for these very strong acids at the top are negative. So you have a negative 11, negative 9, negative 7 for the pKa. That means that the equilibrium constant is going to be 10 to the 7th, 10 to the 9th, 10 to the 11th. And then as you get to Ka's that are negative in terms of their exponents, then the pKa becomes positive. And so down at the bottom of this table, you have pKa's that are very large. That means they're very weak acids. So I could ask you to compare acid strengths by looking at a table of Ka's or looking at a table of pKa's. And you have to know which one, how to interpret that. Okay? All right, so I think that's just what we've talked about here. So anything which has a Ka that is greater than 10 or 100, we would consider to be a strong acid. In other words, there's a lot more products than there are reactants, and essentially it's completely dissociated. If the Ka is somewhere around 10, 1, 0.1, down to about 10 to the minus 4, we call that a moderately strong acid. So HF is a 10 to the Ka, has a Ka of 10 to the minus 4. That's a moderately strong, but it's much weaker than some of the other acids like HI or HCl. HF is a much weaker acid, okay? And then you start getting down below 10 to the minus 5, and these are what we consider weak acids. They still dissociate to give some H3O+. So if you tested them with litmus paper, they would turn litmus paper red. But they're not strong enough to burn you. So for example, vinegar is what? What is a bottle of vinegar? It's about a 5% solution of acetic acid in water. And if you spill vinegar on your hand, does it burn your hand? It smells, but it doesn't burn your hand. You don't jerk it away like if you spilled some hydrochloric acid on your hand. And that has a Ka of about 10 to the minus 5. Most organic acids have Ka's that are roughly 10 to the minus 5. Benzoic acid, acetic acid, all of them are in that 10 to the minus 5 range. And they don't meet the definition of RECRA for being a corrosive. They have pHs that are above 2. They don't, and they also don't meet the definition of DOT because they don't destroy your skin upon contact. They will turn litmus paper red, so they're weak acids, but they're not particularly destructive. So let's see here. What else do we have? So we talked about pKa, and that's basically it. Okay, so now let's actually move to where we can do some calculations. There's also a term that's called mineral acids. You ever heard that before? Mineral acids? Okay, you might run across that in your reading. And mineral acids are either HX type acids or oxy acids. So an HX type acid is one where you have a hydrogen bound to X, where X could be chlorine, like an HCl, or X could be fluorine or iodine or bromine. It's another example of an HX. Well, those are the main HX type acids. An oxy acid is one where you have a central element that's bound to oxygen, and then the hydrogen is bound to oxygen, not to the central element. So here, for example, is perchloric acid, okay? And the actual bonding of perchloric acid is that you have a chlorine in the center, but the chlorine is bound to the oxygen, and then the hydrogen is bound not to the chlorine directly, like an HCl, but it's bound to the oxygen, which is bound to the chlorine. That's what we call an oxy acid. And we have a whole bunch of those oxy acids. So we have nitric acid, sulfuric acid, perchloric acid, phosphoric acid. Those are examples of oxy acids. So both HX acids and these oxy acids are what we call mineral acids. And that's distinguished from carboxylic acids, where we have that COOH bond for the organic functional group of an acid. Now, many of these mineral acids are very strong acids. HCl, nitric, perchloric, very strong. Kas that are very, very large. Okay? Essentially completely dissociated when you dissolve them in water. But that's not always true. So some of these materials are like moderately strong acids. Phosphoric acid, for example, if we look at here's phosphoric acid right here, okay? And it's got a Ka of 10 to the minus 3. So if the Ka is 10 to the minus 3, what does that mean? At equilibrium, what does that mean? Yeah, so there's still an awful lot of H3PO4 molecules left at equilibrium. There's a little bit that is dissociated to give me a hydrogen ion and a H2PO4 minus ion, but most of it is still as H3PO4. So it's a moderately strong acid. It might burn your skin a little bit if you spilled some phosphoric acid on it, but it's not a strong acid like perchloric or hydrochloric is. Now you're drinking phosphoric acid every time you drink a Coke. They put phosphoric acid in there. They don't put very much in there. It's not a high concentration, but we're drinking phosphoric acid every time we drink a Coke. So that's an example of what we call a moderately strong acid. And then when the Ka gets down below 10 to the minus 5, we typically call those weak acids. There's a whole bunch of the weak acids that you can see, okay? So we talked about organic acids are acids that contain the functional group C double bond O, COH. And it's this hydrogen on the COH that's in red right here. It's this hydrogen that tends to come off as an H+. So when I react this with water, what happens is I get H3O+, I'm pulling that hydrogen off, so it's attacking one of the lone pair of electrons on that oxygen atom on the water, and then I get the acetate ion, which is the CH3COO- ion. That's the acetate ion. Or in this, in our equations, we just called that X minus, whatever X happens to be. In this case, it happens to be acetate. So it turns out that if you have this COOH group, it doesn't so much matter what the R group is, whether it's methyl, like in acetate, or whether it's a benzene ring, like in benzoic acid. They all have roughly 10 to the minus 5 as the Ka. So they vary a little bit, but not very much. Now, you can put what are called electron withdrawing groups. So notice here that instead of having CH3, I have CF3. This is called trifluoroacetic acid or trichloroacetic acid. Remember that fluorine and chlorine both have very high electronegativities. They tend to pull electrons towards themselves, right? And so we call these electron withdrawing groups. That means they tend to pull electrons towards themselves. Now in that acetate ion, you have a negative charge. And so when you put those fluorine and chlorines on here, that negative charge tends to get spread over the whole molecule. The CF3 and the CCl3 are going to be much more able to pull that electron density towards itself than a CH3, which doesn't have much electron withdrawing capacity. And so that means that it turns out that you can affect the acidity of this carboxylic acid by putting electron withdrawing groups on that R group. And so CF3, the trifluoroacetic acid, is actually as strong an acid as hydrochloric acid is. It's a very strong acid. Whereas normally acetic acid, we're not particularly worried about its acid strength. But you make trichloroacetic acid or trifluoroacetic acid, and it's a very strong acid because of that electron withdrawal. So in organic chemistry, you can kind of tinker with it. You can kind of dial it in. How many chlorines do I want to put in? How strong an acid do I want to make it? You can dial it in when you're making these different organic chemicals. Okay, so we've talked about strong versus weak acids. We can also talk about strong versus weak bases. And so most strong bases are things like metal hydroxides, like sodium hydroxide, potassium hydroxide, calcium hydroxide. And what that means is that when they dissolve in water, they dissolve completely to produce. If I have 1 molar sodium hydroxide, I have 1 molar hydroxide ion when it dissolves in water. There's not an equilibrium constant. It's just like HCl. If I dissolve 1 molar hydrogen chloride in water, if I have 1 molar hydrochloric acid, I have 1 molar hydrogen ion. If I have 1 molar sodium hydroxide, I have 1 molar hydroxide ion. It's a strong base. So all of the alkali metals and the alkaline earth metal hydroxides are considered strong bases. So if I tell you you've got strontium oxide, calcium oxide, and it's a certain concentration, that's the concentration of the hydroxide. Except for the fact that in the case of calcium hydroxide, notice that if we did that, calcium hydroxide has 2 hydroxides, right? Calcium is a +2 ion instead of a +1. So if I had 1 molar calcium hydroxide, and that's going to dissociate in water to form calcium ions and 2 hydroxide ions, the concentration of hydroxide ion in solution would be 2 molar. It'd be completely dissociated, but since there's 2 moles of hydroxide for every mole of calcium hydroxide, the concentration of hydroxide would be 2. Okay. When we talk about weak bases, then these are things which have an equilibrium constant associated with them. So for example, let's look at ammonia plus water. This is a classic example of a weak base. So here's the basic equation, okay? Ammonia plus water, the ammonia is acting as a Bronsted base, meaning it accepts a proton from water, okay? And where's that proton going? From a Lewis acid base standpoint, where's that proton going in the case of ammonia? That's the electron dot structure for ammonia, right? It's got 3 NH bonds, and then it's got a lone pair of electrons on the nitrogen. What does that lone pair of electrons mean?
It takes one of the hydrogens off of the water.
Okay, so it could be a Lewis base because it could donate a pair of electrons, or it could be a Bronsted base because it can accept the proton. Where's the proton going? It's going after that lone pair of electrons on the nitrogen. You could explain it either way. So the nitrogen in the case of ammonia makes it a base, okay? And the nitrogen in most compounds is going to make that compound somewhat basic. It can vary a little bit, but in most compounds, that nitrogen's got a lone pair of electrons on it, and that's going to tend to make that compound somewhat basic. like in amino acids and proteins and things like that, okay? But it's a weak base. It means that, yeah, there's a tendency for that nitrogen to accept the proton, and when it does, it makes an NH4 plus and a hydroxide ion, right? So that hydroxide is going to make it basic. It means that if you test it with litmus paper, it's going to turn blue. But it's a weak base, so it only accepts a little bit. At equilibrium, if we looked at ammonia plus water at equilibrium, we're still going to have an awful lot of NH3 around. Only a small amount of it's going to be protonated. There's going to be more NH3 than there is NH4 plus because it's a weak base. A little bit of it gets protonated, but not 100%. So we have to talk in terms of an equilibrium constant. Same thing's going to be true here of other types of bases. Here's bicarbonate, which is a weak base. So the bicarbonate ion can accept a hydrogen ion from water to form carbonic acid, H2CO3, and a hydroxide ion. That makes it a base. But it's a weak base, means this equilibrium doesn't go completely. So at equilibrium, there's going to be more bicarbonate, HCO3 minus, than there is carbonic acid at equilibrium. And then down at the bottom, we have the HPO4 2 minus. It's a base. It can accept a proton, but it's a weak base. Okay? So how do we do this quantitatively? So we're going to do some calculations where we calculate the pH of weak acids and calculate the pH of weak bases. So remember the definition of a weak acid, or the definition of pH is pH equals negative logarithm of the hydrogen ion. Okay? And if we have a strong acid, we don't have to worry about it. In the case of a strong acid, whatever the concentration of the acid is, that's the concentration of the hydrogen ion concentration. So if I have 2.5 molar HCl, I have 2.5 molar H+. If I have 0.003 molar HCl, I have 0.003 molar H+. So I just plug in that concentration of hydronium ion into my pH equation, and I calculate the pH. So what would the pH of a 0.003 molar solution of HCl be? 0.003. Well, what's the hydrogen ion concentration of a 0.003 molar HCl?
0.003.
So you just plug in 0.003, hit log, it's minus 2.52, but pH is the negative log, so it's plus 2.52. So the pH of a 0.003 molar HCl solution would be 2.52. That's all you have to do. It's real easy, okay? In the case of a 0.1 molar solution, remember 0.1 is equal to 10 to the minus 1. And remember the logarithm is just whatever that exponent is. So the logarithm of 10 to the minus 1 is minus 1. The pH is the negative logarithm, so the pH would be 1. Okay? So as you go up in pH, you have less and less hydrogen ion concentration. As you go down in pH, you have more and more hydrogen ion concentration. A 10th molar HCl solution has a pH of 1. A 0.003 molar hydrogen HCl concentration has a pH of 2.52. Less hydrogen ion at a pH of 2.52. Making sense? Okay. Now, what happens when we move to a weak acid? Well, in the case of a weak acid, we have to think in terms of an equilibrium. So here's my equilibrium. This is acetic acid reacting with water to produce hydronium ion and the acetate ion. But this equation doesn't go to completion. So if I tell you that I have a 10th molar solution of acetic acid, I can't assume that I have a 10th molar H3O plus concentration because it doesn't go to completion. I have to use the equilibrium constant. So the equilibrium constant is products divided by reactants. Remember, we don't include the concentration of water when we're writing the equilibrium constant. So it's H3O plus times acetate divided by the concentration of acetic acid that remains at equilibrium. Now, that's a lot of unknowns. I have 3 unknowns there, right? I have hydrogen ion, H3O plus, and I have acetate ion. And I have the acetic acid concentration, 3 unknowns. But if I look at it, I can reduce that a little bit. What do I know about the relationship between the hydronium ion concentration and the acetate concentration? You tell me about their relationship.
They're the same.
Yeah, every time I produce an H3O plus, in other words, I'm starting off with acetic acid. I pull off a proton to make H3O plus. When I pull off a proton, what do I make?
Acetate.
I make an acetate. So every time I produce an H3O plus, I produce an acetate. So whatever the concentration of H3O plus is, it's also the concentration of acetate. So let's call that X. X is the concentration of H3O plus. It's also the concentration of acetate. Now, what about the concentration of acetic acid? Well, I said in this equation, let's assume that it's 10th molar. So it starts off as 10th molar. What is it at equilibrium? It started off at 10th molar. Yeah, it started off as 10th molar, but some of it is reacted, right? Some of that acetic acid has lost a proton. How much? How many protons did we produce? We produced X. So the amount of acetic acid left at equilibrium is what we started with, 0.1 minus X, the amount that reacted. So the concentration of acetic acid at equilibrium is going to be 0.1 minus X. So I can plug that into my equation here. This is my Ka expression, and it's simplified now. It's X squared divided by 0.1 minus X. And it's X squared because the concentration of H3O plus is equal to the concentration of acetate. They're the same. Make sense? Now, what do I know about acetic acid? What's the value of Ka? You look it up in the table. It's 1.8 times 10 to the minus 5. 10 to the minus 5, that's a pretty small number. It means acetic acid isn't a very strong acid. So how much X is there really going to be compared to 0.1?
Negligible.
Not very much. So to a first approximation, let's assume that X is small compared to 0.1. Well, if I do that, then 0.1 minus X just equals 0.1, right? If X is small. Now my equation becomes really simple. Ka equals X squared divided by 0.1. Multiply both sides by 0.1. Take the square root, and X equals 1.34 times 10 to the minus 3. And what is X? X is the acid concentration, the H3O plus concentration. So what is pH? It's the negative logarithm of 1.34 times 10 to the minus 3. Plug that number into your calculator, hit log, and you'll get minus 2.87, but the pH is the negative logarithm, so the pH is going to be 2.87. So as a general rule of thumb, if the Ka is 10 to the minus 5 or smaller, then you can ignore X when you're talking about this. If the Ka is down in the 10 to the minus 2, 10 to the minus 3 range, if you ignore it, you're going to not necessarily get the right answer. Can I solve this equation without ignoring X? In other words, this equation right here, can I solve 1.8 times 10 to the minus 5 equals X squared divided by 0.1 minus X? Sure I can. That's a quadratic equation, so I can solve for X, just a little more complicated. So the point is, if you're dealing with weak acids which have Ka's about 10 to the minus 5 or lower, you don't have to use a quadratic equation. If it's a stronger acid than about 10 to the minus 5, then to get a more accurate answer, you need to use a quadratic equation. Make sense? Okay, so notice that we have two 10th molar acid solutions. We had 10th molar HCl, and we have 10th molar acetic acid. The pH of 10th molar HCl is 1. pH of 10th molar acetic acid is 2.83. Same strength, but one's a weak acid, one's a strong acid. They have different pHs. Okay? So under RCRA, would a 10th molar hydrochloric acid solution be considered hazardous waste?
Yes.
Yeah, because its pH is less than 2. But under RCRA, would a 10th molar acidic acid solution be considered hazardous waste? No, pH is above 2. Make sense? So those are the kind of calculations. If you were classifying materials and trying to decide is it a hazardous waste or not, that's the kind of decision that you might end up having to make. Now, let's talk about water. Remember we said that water was an amphoteric compound. It could be an acid or a base. So let's consider just a solution of pure water, nothing else dissolved in it. What's on our, okay, thanks. So when we're talking about pure water, we could imagine that one water molecule might donate a proton to a second water molecule. So think about how this works. We've got an OH bond, right, in the water molecule. That OH bond is broken in the first molecule where we generate a hydrogen ion, an H+. Where does that H+ go? It goes to the lone pair of electrons on the oxygen atom on a second water molecule. So when that H+ goes to a water molecule, it forms H3O+. And when you break that OH bond and you lose an H+, what do you have left? An OH-. So when two water molecules react, you generate an H3O+ and you generate a hydroxide. And so that's the reaction that I've written up here. That's the reaction that shows water is an amphoteric compound. One water molecule is accepting a proton, one water molecule is donating a proton. Now, that equilibrium constant turns out to be very small. It's not 0, but it's very small. Turns out that it's 1 × 10⁻14 at room temperature. So I can write the equilibrium constant for this reaction. It's products divided by reactants, right? So the products are going to be H3O+ and hydroxide ion, and the reactants are water, but we don't include the concentration of water in equilibrium concentration. So K is equal to the concentration of H3O+ times the concentration of hydroxide. Now we give this particular K a special name. We call it KW. That's the acid dissociation constant for water. And it is 1 × 10⁻14. It didn't have to be. Just so happens that water has an equilibrium constant. A Ka for water is 1 × 10⁻14. Okay? So let's solve that equation for the hydrogen ion concentration. What do we know about the relationship in this equation? What do we know about the relationship between H3O+ and hydroxide? Every time I produce an H3O+, what do I produce?
Hydroxide.
So what do we know about them? So let's just call one X and the other is going to be X. So this equation now becomes 1 × 10⁻14 equals X squared. Can I solve for X? Take the square root. Square root of 10⁻14 is 10⁻7. So the hydrogen ion concentration, the H3O+ concentration, is 1 × 10⁻7. Take the logarithm of that. That's -7. Take the negative logarithm, which is the pH, that's 7. Voila. That's why the pH of water is 7. It's not some magical number that somebody decided I liked 7 as a number, so let me just assign that as the pH of water. No, it's because the Kw for water just happened to be 10⁻14. Suppose the Kw for water had been 1 × 10⁻16 instead of 10⁻14. What would the pH of neutral water be in that case? 8. And it could well be, it just so happens that the pH of water is, or the Kw for water is 10⁻14. So that's why we get a scale of 7 as neutral pH. And so anything that has a pH less than 7 we consider acidic, meaning it has more hydrogen ion in it than water does. And anything which has a pH greater than 7 we consider basic, meaning it has more hydroxide in it than water does. That's all. And the further away from 7 it gets, the stronger the acid or the stronger the base would be. Okay? All right. This pH of neutral water is somewhat temperature dependent. Most equilibrium constants will change with temperature, And the same thing's true about Kw. So Kw could be slightly different. It's 1 times 10 to the minus 14 at 25 degrees Celsius, but at 30 degrees Celsius or 40 degrees Celsius, it'd be slightly different, meaning that the pH of neutral water would be slightly different from 7 at a different temperature. So if you've ever used a pH meter, you'll notice there's some kind of temperature adjustment on there. So if you're measuring the concentrate or the pH of water that's not at 25 degrees Celsius, you need to use that temperature control. Otherwise, you'll get the wrong answer. All right, let's talk about how do we calculate the pH of bases. So remember, a base is something that reacts with water to accept a proton, and when it pulls a proton off water, what do you get? You pull a proton off water, what remains behind is hydroxide ion, okay? And so here's my general equation for a base accepting a proton from water to form HB plus hydroxide. And now I can write an equation for Kb. Kb is just products divided by reactants. So it's HB times the concentration of hydroxide divided by B. Just like when I was talking about an acid, it was H3O plus times X minus divided by HA. Okay? Now, what do I know about the relationship between HB and hydroxide? They're going to be equal. So let's call one X and the other is going to be X. So this is going to be X squared divided by the concentration of B. And if I have a number for the value of Kb, then I could solve this equation. So it turns out that, for example, ammonia has a Kb of 1.8 times 10 to the minus 5. So I'm going to plug that in for Kb, and I'm telling you the concentration of ammonia is 10th molar. So it's going to be X squared divided by 0.1 equals 1.8 times 10 to the minus 5. Solve for X, and you get X equals 2.87. Now, excuse me, X equals 1.34 times 10 to the minus 3. But what is X? Here's the difference here. We're doing bases, and we're solving for the hydroxide concentration, right? We're solving for hydroxide, and hydroxide turns out to be 1.34 times 10 to the minus 3. So I can calculate P, what we call POH, which is the negative logarithm of the hydroxide concentration. So plug in 1.34 times 10 to the minus 3 and hit log, and then the negative of that is going to be 2.87. So what I do here is to calculate the POH first. The POH is equal to 2.87. The pH is going to be 14 minus the POH, which is 11.13. So the equation you need to remember is pH plus POH equals 14. So if you know the POH, just subtract it from 14 and you'll get the POH. So for neutral water, what's pH? 7. What's POH? 7 too. And that makes sense because the hydrogen ion and hydroxide are supposed to be equal in neutral water, right? So for calculating the pH of bases, you calculate the hydroxide concentration first, then get POH, then subtract that from 14 and you'll get pH. So would this 10th molar solution of ammonia be considered a hazardous waste under RCRA? Remember the definition under RCRA of hazardous waste? pH was greater than or equal to 12.5. 11 isn't greater than or equal, so it wouldn't be a hazardous waste under RCRA. So one of the questions that I'm going to ask you on the next quiz would be, for example, I give you some different acids or bases and say arrange them in order of increasing acid strength, or in this case, increasing pH. Now, increasing pH means you start with the lowest pH and you get to the higher pH. So the lowest pH is going to be the strongest acid, and the final would be the weakest acid. Okay, so here we're going to go from strongest acid to weakest acid. So what you have to do is to look up Kas and figure it out. Now, sometimes you have to look it up, sometimes you don't. So, for example, 10th molar sodium hydroxide. What do I know about that?
Base.
That's a strong base. So 10th molar sodium hydroxide is going to be 10th molar hydroxide. So in terms of pH, what's the pH of 10th molar hydroxide going to be? So the pOH of 10th molar hydroxide would be what? 1.
So the pH would be 13.
Exactly. So 10th molar sodium hydroxide would have a pH of 13. So that's going to be a really strong base. And then I'm going to have to use equilibrium constants to calculate these other two. And then I could determine which was the strongest base and put them in order. Does that make sense? Okay, so you'll have to use that table that I gave you. They don't have a table like that in your textbook, so use the one that I gave.
Since they're all the same concentration, wouldn't they just be arranged in order?
You could also just look at the table of Kas to arrange them in order. Unless I ask you to actually calculate it, you could just arrange them in order. So remember that the stronger acids are going to be the weaker bases. So let's look at that here just a minute. So what's going on here is that acid strength is increasing from bottom to top, or decreasing from top to bottom. And here, base strength is increasing as you go from top to bottom. So things on the bottom are stronger bases, things on the top are stronger acids, okay? So hydroiodic, hydrobromic, perchloric, hydrochloric, these are very, very strong acids. Now, here's a rule of thumb. There's something called the conjugate base. The conjugate base is what you have left over when you pull the hydrogen ion off. So what's the conjugate base of HI? What do you have left over when you pull a hydrogen off of HI? You're pulling a hydrogen ion off, H+. So what do you have left over? I-. And the conjugate base of perchloric acid, HClO4, would be perchlorate ion, ClO4-, okay? So these are all the conjugate bases. Okay, this is A-, the conjugate bases. So when you have the conjugate base of a strong acid, that conjugate base is very weak. In other words, I- has very little tendency to attract a proton because HI is a strong acid. So if you're HI, you want to lose that acid. You don't want to, if you're I-, you don't want it back. It's like a wife kicking out a husband or something like that. You want to lose the husband, you don't want him back. Not sure where I came up with that analogy, but okay. So the I- doesn't have any tendency to want to grab onto a proton. So it is a very weak base. On the other hand, if we go down to the bottom of this column and we start looking at some of these materials like cyanide or sulfide, okay, these are the conjugate bases of very weak acids. So if you're HCN, that's a very weak acid. So cyanide's a pretty strong base. It has a tendency to grab a proton. Sulfide, S-2, is a pretty strong base, has a tendency to grab a proton. Does that make sense? So you can talk about the acid strength of the acid, or you could talk about the base strength of the conjugate base. The conjugate base of a strong acid is weak. The conjugate base of a weak acid is much stronger. So I could say compare the base strength of sulfide ion versus iodide ion. S2- versus I-. Which would be the stronger base?
S2.
S2-, because it's the conjugate base of a weak acid. So it's a much stronger base. Okay? Does that kind of make sense to you? Don't you wish you could go back and do the general chemistry over again? Hopefully you could just zoom through it and all make sense. Be easy. All right, so I think we've covered what we need to in this one. So as a general rule, when we have metal oxides, they're going to be basic, like sodium oxide, magnesium oxide, calcium oxide. These oxides will react with water to produce hydroxides that are completely dissociated, like sodium oxide reacts with water to produce sodium hydroxide. They will also react with acids. Because they're bases, they react with acids. What is Fe2O3? What's another name for that? What would the IUPAC name be for Fe2O3? Okay, Fe2O3 means it's an iron plus 3 ion, right? So that would be iron, Roman numeral 3 oxide, or ferric oxide, and another name for that is rust. That's what rust is, Fe2O3. And that is going to tend to be basic. The oxides of metals tend to be basic, meaning they react with acids. And so rust will dissolve an acid. And here's the equation for dissolving an acid. So metal oxides tend to react with acids because they tend to be basic. Whereas non-metal oxides, such as sulfur dioxide, tend to be acidic. They react with water to produce H2SO3, sulfurous acid. SO3 reacts with water to produce H2SO4, sulfuric acid. That's where we get acid rain. So non-metal oxides tend to be acidic, metal oxides tend to be basic. Okay, so read through this. We've got a couple more modules that we'll cover on Thursday. Hopefully by the end of the week, you'll know everything there is to know about acids and bases.